Integration of SpaceX's Starship technology by 2026, key innovations and a projected $10 billion investment in launch capabilities. Overview. SpaceX is on the brink of a transformative phase in space exploration with its Starship program backed by a projected $10 billion investment aimed at achieving full technological integration by 2026. The primary goal of this initiative is to enable rapid reusability for both Starship and its Super Heavy booster, which are crucial for significantly reducing launch costs and increasing the frequency of flights. Key innovations and developments. 1. Reusability of launch vehicles. Starship is engineered to be fully reusable. This contrasts sharply with current launch costs associated with SpaceX's Falcon rockets, which hover around $2,720 per kilogram. The anticipated cost for the fully reusable Starship could drop to between $100 and $200 per kilogram, covering only fuel and maintenance expenses. This paradigm shift in cost structure is expected to make space more accessible than ever before. 2. Enhanced launch capacity. SpaceX is establishing a state-of-the-art production facility dubbed the Starfactory, which aims to assemble one Starship per week. Coupled with additional launch sites at Cape Canaveral, SpaceX is targeting a launch cadence that could exceed 44 flights annually. 3. Expanded use cases. The reduced costs associated with Starship will open the door to a range of new activities in space. This includes rapid suborbital deliveries, extensive deployment of satellites for megaconstellations like Starlink, and support for NASA's Artemis program, which aims to return humans to the Moon. Timeline of events. April 2023, the first full flight test of Starship occurred but ended with a rapid unscheduled disassembly shortly after launch. October 2023, a significant milestone was reached when the fifth test flight demonstrated the recovery of the Super Heavy booster and a controlled splashdown of the Starship's second stage. 2024 to 2026, SpaceX aims to conduct uncrewed missions to Mars by 2026 and potentially crewed missions by 2028, with the long-term goal of establishing a permanent human presence on the Martian surface. Challenges and solutions. Regulatory hurdles. SpaceX faces significant regulatory challenges in obtaining launch licenses, primarily due to environmental concerns. This has delayed flight test schedules and prompted extensive discussions with regulatory bodies. The company emphasizes that many of these delays stem from the lengthy bureaucratic processes rather than safety concerns. Technical hurdles. Achieving full reusability for Starship presents a multitude of technical challenges. SpaceX has adopted a rapid test and learn approach, putting flight hardware into operational environments frequently to gather data and refine designs. This iterative development process has been instrumental in progressing towards the ambitious reusability goal. Common themes across sources. Importance of reusability. There is unanimous agreement across sources on the critical importance of achieving full reusability for Starship. This is seen as essential for lowering costs and enhancing launch capabilities. Support for NASA missions. The dual focus on supporting NASA's lunar missions while preparing for Mars colonization is a recurring theme in discussions surrounding Starship. Regulatory challenges. The regulatory environment and its impact on timelines are acknowledged in all discussions, highlighting the tension between innovation and compliance. Differentiation in perspectives. Source 1 emphasizes the internal challenges facing SpaceX, particularly the regulatory hurdles and safety measures that are impacting timelines. This source provides a detailed account of the bureaucratic challenges and public safety measures being implemented. Source 2 takes a broader view of the implications of Starship's capabilities for future space missions and economic activities. It expresses optimism about the potential for Starship to enable large-scale operations in space, including resource utilization on the Moon. Conclusion. SpaceX's ambitious plans for the integration of Starship technology by 2026 hinge on achieving rapid reusability and cost-effectiveness. If successful, these developments could reshape commercial and governmental space endeavors, heralding a new era of exploration and resource utilization. The ongoing innovations and challenges faced promise to alter humanity's relationship with space, making it more accessible and sustainable for future generations. The integration of Starship technology is not merely about reaching new heights in space, it is about laying the foundation for a future where humanity can thrive on multiple planets. With a clear vision and the determination to overcome existing hurdles, SpaceX is poised to lead this charge into the cosmos. The integration of SpaceX's Starship technology by 2026 is marked by several key innovations, especially in the area of reusability, which could significantly alter the economics of space launch operations. The anticipated $10 billion investment aims to achieve full operational capability, emphasizing the importance of reusability in reducing costs and increasing launch frequency. One of the most counterintuitive aspects of this development is the extent to which reusability can reduce launch costs. Current projections estimate that the cost per kilogram to orbit could drop from $2.720 with existing Falcon rockets to as low as $100 to $200 with Starship. This drastic reduction hinges on the ability to reuse almost all hardware involved in the launch, which contrasts with traditional models where rockets are typically single-use after each launch. Moreover, the establishment of a production facility dubbed the Starfactory aims for an ambitious output of 1 Starship per week. This is in stark contrast to the current production rates of Falcon rockets, which could open up pathways for unprecedented flight frequency. The plan includes multiple launch sites, potentially allowing SpaceX to exceed a cadence of 44 flights per year, which could fundamentally change how often payloads can be launched into space. Another counterintuitive point is the potential for urgent deliveries via suborbital flights. These capabilities, previously deemed impractical due to high costs and limited frequency of launches, could become viable, enabling rapid deployment of supplies or equipment across different parts of the Earth, particularly for emergency situations. This reflects a shift in how space capabilities can intersect with terrestrial needs. The technological timeline, which includes uncrewed missions to Mars by 2026 and crewed missions by 2028, also emphasizes an aggressive approach to space exploration. The goal of establishing a sustainable human presence on Mars is ambitious, especially considering the challenges of such an endeavor. The focus on Mars over the Moon, despite NASA's Artemis program aiming for lunar missions, represents a strategic choice that might seem counterintuitive. Prioritizing Mars colonization could overshadow the Moon's potential as a launch point for deeper space exploration. Furthermore, the regulatory challenges SpaceX faces in obtaining launch licenses can be seen as a paradox. While the pace of technological development and the hardware itself can advance rapidly, the bureaucratic processes lag behind, highlighting a mismatch between innovation speed and regulatory frameworks. For instance, SpaceX's ability to conduct numerous flight tests and learn from failures quickly contrasts with the time-consuming nature of environmental assessments and licensing processes, which could hinder progress. Lastly, the emphasis on environmental concerns in the launch process, particularly regarding the water-cooled steel flame deflector, reveals a counterintuitive narrative. SpaceX argues that its operations are environmentally compliant and that the technologies in place do not harm the environment, challenging public perceptions driven by concerns over pollution and ecological impact. The fact that SpaceX has implemented extensive mitigations and monitoring practices while simultaneously facing regulatory pushback based on environmental grounds illustrates the complexities involved in balancing innovation with public safety and environmental stewardship. In summary, the integration of SpaceX's Starship technology by 2026 is not just a technical endeavor but also a transformative shift in how humanity approaches space exploration, economics, and environmental considerations. The counterintuitive insights into cost reduction, production scalability, and regulatory challenges provide a nuanced understanding of the challenges and opportunities ahead for SpaceX and the broader space industry. The report on SpaceX's integration of Starship technology by 2026 highlights several key innovations that many may overlook, yet these elements hold significant implications for the future of space exploration and commercial activities. Below are the important aspects that deserve special attention. 1. Rapid reusability and cost reduction. The Starship is designed to be fully reusable, which is a fundamental shift from the current rocket launch paradigm where most components are discarded after a single flight. The anticipated reduction in launch costs, from approximately $2.720 per kilogram with Falcon rockets to between $100 and $200 per kilogram for Starship, will drastically change the economics of space travel. This could enable a wider range of activities from scientific exploration to commercial ventures in space. The significance lies not just in cost savings but in the potential to democratize access to space, allowing more entities, including smaller companies and nations, to participate in space activities. 2. Starfactory initiative. The establishment of the Starfactory production facility aims to build one Starship per week. This level of production is unprecedented in the aerospace industry and indicates a shift towards an industrialized approach to space travel. The implications of having such a rapid manufacturing capability extend beyond merely increasing launch frequency. It could lead to innovations in logistics, supply chain management, and even workforce training in advanced manufacturing techniques. The sheer scale of production could also act as a catalyst for economic growth in the surrounding regions. 3. Potential for new use cases. The ability to conduct urgent deliveries via suborbital flights, increased satellite deployment for megaconstellations like Starlink, and support for NASA's Artemis program represents a diversification of potential applications for space travel. This versatility is significant as it showcases the utility of Starship technology across various sectors, commercial, governmental, and scientific. Such broad applicability could foster collaboration among diverse stakeholders, leading to innovations in new business models. 4. Lunar and Martian exploration. The report outlines SpaceX's plans to support NASA's Artemis program and to establish a permanent human presence on Mars by the late 2020s. The strategic focus on lunar and Martian exploration reflects a long-term vision for humanity's expansion beyond Earth. The significance of this ambition is profound. It aligns with global scientific interests in understanding other celestial bodies and could lead to breakthroughs in multiple disciplines such as biology, physics, and engineering. Furthermore, the potential for resource utilization on the Moon, such as extracting and using water ice for fuel, could reshape our approach to sustainable space exploration. 5. Regulatory challenges. The report mentions ongoing regulatory hurdles that SpaceX faces, particularly concerning environmental concerns related to launch licenses. This aspect is crucial yet often overlooked when discussing the technological advancements of companies like SpaceX. Regulatory frameworks will need to evolve in tandem with technological progress to ensure safety and environmental sustainability. The challenges faced by SpaceX highlight the complexity of balancing rapid innovation with regulatory compliance, pointing to a need for dialogue between private companies, government agencies, and environmental stakeholders. 6. Impact on global space economy. With the potential for drastically reduced launch costs and increased launch frequency, SpaceX's initiatives could stimulate a burgeoning global space economy. This could lead to the emergence of new markets such as space tourism, in-orbit manufacturing, and asteroid mining. The significance lies in the transformative potential for global economic structures and job creation, as well as the role of private enterprise in driving space exploration. 7. Sonic boom and public perception. The report discusses the sonic booms generated during Starship landings and the public's reaction to these phenomena. The significance of addressing community concerns about noise pollution cannot be understated. As SpaceX aims to increase flight frequency, managing public perception and environmental impact will be crucial for maintaining social license to operate. This aspect speaks to the broader challenges that come with advancing technology in populated areas. 8. Technological innovations. The technical advancements in propulsion systems, guidance, navigation, and control mechanisms are essential for the success of the Starship program. Each test flight provides critical data that informs future improvements. The iterative design process employed by SpaceX is significant as it contrasts with traditional aerospace development practices, which often follow a more linear and less flexible approach. This shift could lead to faster technological advancements across the industry. In conclusion, while the report outlines impressive technical feats and ambitious goals, it is the underlying implications of these developments, cost reductions, production capabilities, regulatory challenges, and the expansion of the global space economy that merit close attention. These factors collectively signify a pivotal moment in space exploration where the barriers to entry are lowered and new opportunities for innovation and collaboration in the final frontier are created. The integration of SpaceX's Starship technology by 2026 could indeed mark the dawn of a new era in human spaceflight and exploration. 1. Reusability and cost reduction. The cornerstone of SpaceX's Starship technology lies in its fully reusable design, which is expected to reduce launch costs significantly, from around $2.720 per kilogram with Falcon rockets to a projected $100 to $200 per kilogram for Starship. This is achieved by reusing all components of the launch system, thus only incurring costs for fuel and maintenance. Such cost reduction is pivotal for increasing the frequency of launches and enabling new activities in space such as urgent deliveries and expansive satellite deployments. 2. Launch capacity enhancement. SpaceX plans to establish a Starfactory that will have the capability to assemble one Starship per week with additional launch sites at Cape Canaveral. This ambitious infrastructure aims to exceed a launch cadence of 44 flights per year, which is essential for meeting the growing demand for satellite launches and other space missions. The enhanced capacity will not only support commercial ventures but also governmental projects like NASA's Artemis program. 3. Support for NASA's Artemis program. Starship is integral to NASA's Artemis program, which aims to return humans to the Moon and establish a sustainable presence there. SpaceX is developing a specialized lunar landing version of Starship that will facilitate this mission. The collaboration signifies a crucial step in human exploration, laying the groundwork for future missions to Mars. This role emphasizes the dual governmental and commercial applications of Starship technology. 4. Potential for new economic activities in space. The implications of Starship's low-cost and high-frequency launches extend beyond traditional space exploration. With the capability for in-orbit refueling and the transport of large payloads, Starship could enable the establishment of a permanent human presence on the Moon, facilitating resource extraction and lunar manufacturing. This could lead to a new era of space-based economies, including the construction of solar power satellites and other commercial space platforms, which could fundamentally alter humanity's relationship with space and its resources. 1. Apollo program and the lunar landing. 1961 to 1972, the Apollo program initiated by NASA aimed to land humans on the Moon and bring them safely back to Earth. It culminated in the historic Apollo 11 mission in 1969 when astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface. The program not only showcased significant advancements in rocket technology and space travel but also established a legacy of human exploration beyond Earth. The lessons learned and technologies developed during Apollo paved the way for future space missions, including potential crewed missions to Mars. 2. The Space Shuttle Program. 1981 to 2011, NASA's Space Shuttle program was a groundbreaking initiative aimed at developing a reusable spacecraft for various missions, including satellite deployment, space station construction, and scientific research. The program's ability to reuse shuttle components significantly reduced costs and increased the frequency of missions. The shuttle fleet completed 135 missions facilitating the construction of the International Space Station ISS and advancing space science. However, the program also faced challenges, including the tragic losses of Challenger and Columbia, which highlighted the complexities and risks of human spaceflight. 3. The Mars Exploration Program 2004-present. NASA's Mars Exploration Program has involved numerous missions aimed at exploring the Martian surface and atmosphere. Notable missions include the Mars rover missions Spirit, Opportunity, Curiosity, and Perseverance, each contributing invaluable data about Mars geology, climate, and potential for past life. The program has laid the foundation for future human exploration of Mars, with ongoing research into the feasibility of sending humans to the planet. The technology and knowledge gained from these robotic missions are vital for developing the capabilities needed for eventual human settlement on Mars. By 2026, SpaceX's Starship technology is projected to significantly transform the space industry, driven by a remarkable investment of $10 billion aimed at achieving full integration and rapid reusability of its launch capabilities. The following predictions outline key innovations, anticipated developments, and broader implications for space exploration. Key innovations. 1. Full reusability. A cornerstone of Starship's design is its complete reusability. This advancement is expected to lower launch costs dramatically, potentially from the current Falcon 9 cost of $2,720 per kilogram to as low as $100 to $200 per kilogram. This shift will enable a new economic landscape for space activities, making missions financially viable that were previously unfeasible. 2. Increased launch capacity. SpaceX plans to establish the Starfactory, a production facility capable of building one Starship per week. Coupled with multiple launch sites including Cape Canaveral, this could facilitate a launch frequency exceeding 44 flights annually. This high cadence is crucial for supporting burgeoning satellite constellations like Starlink and could enhance commercial spaceflight opportunities. 3. Innovative use cases. As costs decline, new applications for space travel will emerge. Starship could enable urgent delivery services via suborbital flights, rapid satellite deployment, and support missions for NASA's Artemis program aimed at returning humans to the Moon. Projected developments. 1. Milestones leading to 2026. 2024 to 2026, SpaceX aims to undertake uncrewed missions to Mars by 2026, with crewed missions potentially following in 2028. This timeline aligns with NASA's plans for lunar exploration and Mars missions, indicating a collaborative effort in human space exploration. Technological improvements. Continuous improvements in rocket design and functionality will be essential. SpaceX's iterative testing approach has already demonstrated advancements in recovery techniques, such as successfully catching the Super Heavy booster mid-air. 2. Regulatory navigation. While SpaceX faces challenges related to environmental regulations and launch licenses, it is expected that successful navigation of these hurdles will contribute to a more streamlined regulatory framework for commercial space launches. Broader implications. 1. Economic impact. The reduction in launch costs and increased frequency of flights could lead to a boom in the commercial space sector, paving the way for a new era of satellite communication research and exploration. Companies and governments may invest more heavily in space initiatives, spurring economic growth and technological innovation. 2. Lunar and Martian colonization. Starship's capabilities may facilitate the establishment of a permanent human presence on the Moon and Mars. The Moon could serve as a launchpad for deeper space exploration and resource utilization, especially with anticipated discoveries of water ice for sustainable living and fuel production. 3. In-space manufacturing and energy production. Looking ahead, the utilization of lunar resources could lead to the construction of large solar power satellites addressing energy challenges on Earth. Moreover, the prospect of robotic manufacturing in space could foster technological innovations, creating an in-space economy by the 2030s. 4. Global collaboration and competition. As SpaceX enables broader access to space, international partnerships may strengthen. However, competition for resources and influence in space could also escalate, necessitating new frameworks for cooperation in addressing challenges such as space debris and planetary protection. Conclusion: SpaceX's ambitious plans for Starship technology integration by 2026 signify a pivotal moment in space exploration. The expected advancements in reusability, capacity, and cost-effectiveness promise to reshape the industry, opening new frontiers for human activity beyond Earth. As we move toward this transformative era, the potential for economic, scientific, and societal advancements is boundless, heralding a new age of exploration and innovation in space.